Okay, we are picking up where we left off. This is the second video to cover the lecture for Thursday, March 5th. Where we left off was we had written down the full joint posterior, which is right here, but this is not the model we're going to draw from. Well, rather than trying to draw from the joint distribution of beta naught, beta 1, and sigma squared, we're of course going to do a Gibbs sampler where we step through those. And so we need to know the full conditionals of each of those guys. So that's the goal of this video. Let's get through these full conditionals. The first full conditional of sigma squared is pretty straightforward because we know that sigma squared given our data y and mu is, assuming that we have an inverse gamma prior, this posterior we have seen is an inverse gamma where the first parameter is n over 2 plus a, and the second parameter is b plus 1/2 the sum from I equals 1 to n of yi minus mu. Now, so I should say, we know this from before. This is the case when we have a constant mean mu. Now, of course, we have jumped over to the simple linear regression setting. And so what's changed here? Well, if I'm drawing from the conditional, I'm gonna assume I'm trying to work for the posterior for sigma squared given the data and the other parameters, which in this case are beta naught and beta 1. So sigma squared given the data, beta naught and beta 1, this of course is going to be inverse gamma. And the mu that we saw before only appears there. If we go back to and look at our simple linear regression model, our mean for our yi is equal to beta naught plus beta 1 xi. And so we can just plug that in essentially for our mean. So our inverse gamma is going to have the first parameter being n over 2 plus a. It's going to have the second parameter being b plus 1/2 summation from I equals 1 to n of, oh, I'm missing a squared here, sorry. It's sum of yi minus mu squared. So down here it's going to be yi minus beta naught plus beta 1 xi, whole thing squared. So here is the first parameter of our inverse gamma. Here's the second parameter of our inverse gamma, given the data, which would go in here, and given the explanatory variable xi, assuming we know beta naught and beta 1, which if we're in the Gibbs sampler situation, we have current values for beta naught and beta 1 that we would plug in. A and B are hyperparameters of the inverse gamma that come from our specification of the prior. And so we've got everything we need to determine what the first parameter of our inverse gamma is, the second parameter of our inverse gamma. And so what we're able to do is when I want to draw from this posterior distribution, I can just use R inv gamma, where the first parameter is that n over 2 plus a. The second parameter goes in just as we've said, that's just a number for any given value of beta naught and beta 1, and we could draw from that. So that piece is going to be relatively straightforward. Okay, now we want to get the full conditional for beta 1. So we want to know the posterior distribution of beta 1 given our data given sigma squared and given beta naught. This is the posterior distribution that we want to draw from. Now, this is going to be pretty challenging. If you remember the conditional for the in the module 4 notes when we were trying to draw the conditional or draw the posterior distribution, write down the posterior distribution for mu given sigma squared, that was pretty involved. Now this having beta naught in here is going to make that even more involved. So this guy, we're going to have to write this down as our posterior. Let me just go ahead and put a P out there to talk so that we're talking about posterior density. The posterior density is going to be proportional, of course, to our likelihood times our prior. And so, in fact, let me cheat and let's go back here a few slides. Let's see, this is the one. We wrote down the joint posterior for all three parameters. That's what we see right here. Now, if beta naught were given and sigma squared were given, then those are numbers. Or you can think of it in the context of the Gibbs sampler. If I'm drawing for beta 1, if I'm drawing a value for beta 1, I have current values for beta naught and for sigma squared. And so we can look at the beta naughts and the sigma squareds as being just numbers. So this is just a number and I can ignore it. This is just a number and I can ignore it. And this is just a number and I can ignore it. And all I am left with are the two expressions that we see there on the slide. So the first step in getting our full conditional will be to just copy what's left there. And so we get so our posterior is going to be proportional to, let's change that color. All right, our posterior is going to be proportional to e to the -1 over 2 sigma squared, summation I equals 1 to n of yi minus beta naught minus beta 1 xi squared. You'll see that what I've done here is I've just distributed that negative sign through. And then what we have is we have to multiply by our prior, and that's going to be e to the -1 over 2 tau squared beta 1 squared. So if you look at this expression and we go back here, you should see that I have the same thing written in both spots. Okay, now this gets tricky mathematically. The math isn't hard, but it can be hard to keep things straight. The argument of our posterior density is beta 1. And so we're going to want an expression that's kind of written in a familiar form for beta 1. And so what we want is something of the form e to the -1 over 2, I'll call it v, beta 1 minus m squared. Eventually, we're going to have a mean, which I'm calling m. We're going to have a variance which I'm calling v, and the argument of my function is going to be beta 1 because this is a posterior for beta 1. Now, in the module 4 notes, we basically started from here and we got rid of another normalizing constant. And we said that another way of writing this, this is proportional. Instead of a squiggly arrow, let me just say proportional here. This is proportional to e to the negative 1 over 2v of beta 1 squared minus 2 beta 1 m. What we saw was starting from something like this, we could do some simplification. We could kill off a constant of proportionality and we could write this. And so if we can come up with an expression that looks like this, then whatever is here will be our mean, whatever is there is our variance. So our goal is to take this thing up here and make it look like this expression that I have written down here on the lower right. Okay, so let me, I'm just gonna I'm going to simplify things a bit. I have an e to the stuff times an e to the stuff. That's e to the stuff plus stuff. Each of these things has a negative 1/2 in it, so I'm going to pull that out. And the reason I'm going to pull that out is, of course, that I want it to look like this expression here. So I can say that my posterior up there in blue is proportional to e to the negative 1/2. And then what I have is in my first term, I have a 1 over sigma squared still there. I have this summation from I equals 1 to n of yi minus beta naught minus beta 1 xi squared. And then I have a plus, I have a 1 over tau squared, which I could write as tau to the negative 2, or you could leave it as 1 over tau squared, and I've got a beta 1 squared. So hopefully you're seeing that this expression here is just combining terms and pulling that 1/2 out. Okay, now this part is a little tricky when you look at it, but the important part is the beta 1. And so what I'm going to do is I'm going to treat this whole thing as one big number, that yi minus the beta naught. I'm going to treat that as a number, and then what I'm going to do is I'm going to FOIL this thing out. Okay? So doing that gives me e to the negative 1/2. I still have my 1 over sigma squared. I still have my sum here. And then my first term is going to be yi minus beta naught squared. My cross term is going to be minus 2 yi minus beta naught times beta 1 xi. And my last term would be plus beta 1 squared xi squared. So all we've done is we have taken this and we've FOILed it out, where the first term is this thing in parentheses. Now, of course, I still have this, so let me just tack that on. Plus tau to the negative 2 beta 1 squared. Okay. Hopefully, so far so good. Now, let me just copy and paste this over to the next slide. All right, so this expression is exactly what we had on the previous slide. And here's, if we focus on our goal, what we're going to do is we're going to need a beta 1 squared term, and we're going to need a term with just the beta 1s, and everything else is going to be a normalizing constant. And so when I look at this first term doesn't have a beta 1 at all. This term has a beta 1 to the first power, and both these terms have a beta 1 squared. So I'm going to just order things where I've got the beta 1 squareds in the front, I have the term with beta 1 in the middle, and I have the term that doesn't have a beta 1 at the end. So let me do that. Okay, whoops. All right, so this is proportional to e to the negative 1/2. I have 1 over sigma squared, or sigma to the negative 2, if you want to write it that way. I have the sum from I equals 1 to n of the beta 1 squared xi squared. Basically what's happening there is this sum gets applied to all three of these things. I want my beta 1 squareds in front. And then I'm going to add on my tau to the negative 2 beta 1 squared. The sum is not getting applied to that piece. But what we have now is a term with our beta 1 squareds in it. Okay, now I want the term with just my beta 1s. And that's going to be, I have this, the sum is getting applied, and in fact, I should have said this 1 over sigma squared is getting applied to all three things as well. And so this middle term is going to be minus 2 sigma to the negative 2 sum I equals 1 to n of yi minus beta naught. And then I have my beta 1 xi. Okay. And then I have this, my last term would be a plus sigma to the negative 2 sum from I equals 1 to n of yi minus beta naught squared. Now I have e to the stuff plus stuff plus stuff. Importantly, this thing does not have any beta 1s in it. I apologize that this isn't a little bit more clear, but this is definitely a beta naught here. This is just a number. This is just a constant of proportionality. It might, if you prefer, you can think of this as e to the stuff times e to this stuff. We can break it up as a product. Let me just go ahead and write it that way. I'm going to use a little cut and paste power here to do that. Okay, so I can write it this way. I can say this, and I can say times e to the negative 1/2, because that part is going through to this last term of this stuff. And this is just a number. And so what we can do is we can kill that off. Okay? So I'm going to carry this term, this expression. Oops. I'm going to carry this expression over to my next slide. Right like that. And okay, now remember, our goal is we want to have a beta 1 squared all by itself. And then we want to have a 2 beta 1 times stuff. So the next step is going to be to get this beta 1 squared all by itself. Now notice, of course, beta 1 doesn't have an I in it, so I can pull it out of the sum, and I can pull it out of that term as well. And so this expression is e to the negative 1/2 sigma to the negative 2 sum I equals 1 to n xi squared plus tau to the negative 2. All of that is, oops, sorry, I did that wrong. This sigma squared is, I've written it a little strangely here. This sigma squared is tied only to this term. It's not getting applied to the tau squared term. So let me just rewrite that a little bit. Let me tie it a little more closely there. All of that is being multiplied by beta 1 squared. I'm going to also pull a beta 1 out of this second term. It's not really going to change it a whole lot, but you know, the sum is being indexed by I. So this term changes with I. The xi changes with I. But the beta 1 does not. So I can pull that out of the sum. And what I end up with is minus 2 sigma to the negative 2 sum I equals 1 to n yi minus beta naught xi that whole thing times beta 1. Okay, now if we think about our goal again, let me flip back. We need to have beta 1 all by itself. We don't. So what we're going to do is we're going to, that stuff that's being multiplied by beta 1 in our expression, we're going to call v. So we're going to say v equals Sigma to the negative 2, sum from I equals 1 to n of the xi squareds plus tau to the negative 2 inverse. The reason I throw that negative 1 on is I want the v to be in the bottom. So if I well, actually, I'm not going to do that. Let's leave it like that. So if I put sorry, let me go ahead and write it that way. Maybe it's clearer to see. So this expression above, this whole line here, I'm going to write this way. So I can write that as e to the negative 1/2. This is v inverse beta 1 squared minus 2 beta 1 sigma squared summation from I equals 1 to n of yi minus beta naught xi. Okay, let's see if I can explain what I've done. If I call v this thing to the negative 1, this piece up here, which doesn't have a negative 1 in it, has to be inverted, which is why I've got this v to the negative 1. The reason that it might be easier to see here is now what I'm going to do is I'm going to pull this v to the negative 1 out and put it in the bottom where I want it. Now, if I pull a v to the negative 1 out of here, I also, and move it outside this curly bracket, I also got to pull one out of here. And it's not there. So instead what I'm going to do is I'm going to insert a v so that I can pull a v to the negative 1 out. And so we get is proportional to negative 1 over 2v curly bracket beta 1 squared minus 2 beta 1 v sigma, this should be to the negative 2, sum I equals 1 to n of yi minus beta naught xi. So importantly, this v appeared here because it cancels out with that. And we pulled it out of this, leaving our beta 1 squared alone, just as we wanted it to be. And it may not look like much, but we're actually exactly where we want to be. Because our goal was to get beta 1 by itself and to have 2 times beta 1 times stuff, which we call the mean. Well, if I come back here, I have 2 times beta 1 times stuff, which I'm going to call the mean. And so our v, let me just cut and paste so that we can see it more clearly on the next slide. Okay, here is our expression. What we're going to do is we have already said that v equals sigma to the negative 2 sigma to the negative 2, sum I equals 1 to n xi squared plus tau to the negative 2 inverse. And we just said our mean from our expression before, we wanted 2 times beta 1 times the mean. So our mean, m, is going to equal v sigma to the negative 2 summation from I equals 1 to n of yi minus beta naught xi. If I want to not leave this in terms of that v here, we can put this expression into there, and what we would end up with is m equals sigma to the negative 2 summation I equals 1 to n of yi minus beta naught xi, and v sigma to the negative 2 summation I equals 1 to n xi plus tau to the negative 2. So we've done it. We've done it. Pat yourself on the back. What we have is remember where we started. We started way back here saying, I want the posterior of beta 1 given my data and given the other values of my parameters. We said that that was equal to the likelihood times the prior, and we did a lot of math and even more bookkeeping, but we got there. We got to an expression which we recognize is the normal density in disguise. It's of this general form. This is the normal density in disguise, or at least it's proportional to the normal density. So our posterior of beta 1 given our data, given beta naught, and given sigma squared, is distributed normal with a mean of m and a variance of v, where we have told you what m is and what v is. And so everything in m and v are just numbers. If I look at v, sigma squared, well, you're saying that's not a number. That I don't know that, but in our Gibbs sampler, we have a current value for sigma squared. We have the prediction or the explanatory variables, the xi's. Tau is fixed as a hyperparameter. Likewise, beta naught has a current value, and so this is just a number, this is just a number. If I want to draw from my full conditional, I can just do R norm draw one value with a mean of m and with a standard deviation being the square root of the variance. And so I can get my draw for my Gibbs sampler immediately from there. All right, we did it. It was not easy, but we found the full conditional for beta 1. You can figure out the full conditional for beta naught. It's going to be very similar. You're going to end up with an expression that looks like this, and this is very likely going to show up on a homework problem. Hopefully you're feeling good about this. We have everything we need to implement our Gibbs sampler. So this is just stepping through those full conditionals that we've just specified. We can loop through this again and again and again and again. We get a chain consisting of 3 elements, a sigma squared, a beta naught, and a beta 1. And we can do our diagnostics for the elements of the chain. And that's what we will do in the coming slides. Okay, so great. I'm going to cut this video off here.